Okay, earlier we have mentioned that a material that is having elastic property, it will actually return to its original shape and size once you remove the load that you apply on it. Let's say you have a spring where you put a mass on it, and then it extended down. So after that, when you remove it, it went back to its original length. Okay, so let's think of what happened when we stretch the material further. So we put more weights on it. Okay, just to test to see what is happening, what will happen. Okay, and after we put many weights and it still haven't snapped, and then we remove that, so what will happen? So definitely we are not talking about the elastic behavior here. It definitely will not be elastic anymore. Then what happened is, after it passes the elastic limit, it will perform plastic deformation. So plastic deformation is like just now we said that the spring we add more mass inside, or we add more weights inside, right? So at a certain point, just like the practical that you did with the springs, so some of the spring doesn't look nice anymore. They are like a bit space in between the coils of the spring, right? So that's because they are overstretched already, which means that they cannot go back to their original length anymore. Basically it's not very useful already. Okay, so this is the two things that you need to remember. Before the elastic limit or within the elastic limit, it will deform elastically. Okay, we call elastic deformation. That's before the elastic limit, and after the elastic limit, it will have plastic deformation. Okay, that is, after the elastic limit, it will not go back to its original length, or we say that the deformation is permanent. Okay, deformation will be permanent. So let's look at one of the example graph of a typical steel or typical metal. Okay, it looks like this. This is, of course, is plotted after the test is done. Okay, there are some information here that I want you to remove actually. So first of all, let's remove this word U point. This is more on engineering purpose. So we have you can see the plastic behavior and elastic behavior and plastic behavior here, and B is the elastic limit. Okay, I just draw a line here just to split that. So before that will be elastic deformation, after that will be plastic deformation. Okay, then you notice that there is another point here called the proportionality limit. All right, we have seen this word in the Hooke's law. We have seen this in the Hooke's law basically. Okay, and then we have this word elastic limit. So these 2 points is different. You have to understand it. For some of the material, these 2 points are actually the same point, but they are actually slightly different in the sense that, let's look at proportionality limit again. So that is where the point after which it will not follow Hooke's law anymore. So before this point, it is a straight line. So you can see that this is a straight line because it follows the Hooke's law, or it obeys the Hooke's law. And after that point, there's a small region here. Let me use a different color because all looks the same. So there's a small region here from from proportionality limit all the way to elastic limit. So this small region here is actually a curved line. So if you have passed the proportionality limit, it will not obey Hooke's law, yes, but however, and when you unload the mass or the weights that you put on it, it will actually still go back to the original position or original length. Okay, it will not have permanent deformation. Okay, so that's something that you have to take note. Yeah, so after proportionality limit, yes, the thing will still will still perform elastic deformation, it will still go back to the original length. However, it won't follow Hooke's law. Okay, it's after elastic limit that it won't go back to the original length. Okay, which is the plastic deformation. All right, so then you might be asking, so if let's say it doesn't go back to the original length, how would the graph looks like? Let's say I unload the weight slowly, and then I want to plot the graph. How would it look like? Okay, so first of all, let's try to clear the screen first, because a bit messy here. So let's say at point C. Let's say at point C, okay, we load it and then we stop here. Okay, we don't put any further load on it, and then from there we slowly remove. So slowly remove means that the stress is now going to go down. So stress go down, and then you can see that it will actually, if you plot that again, it will actually go down, and this with this line all the way down to when you put when you remove all and it becomes zero stress. So it will have a permanent strain here. Okay, so that line, a very common behavior or a very common properties that you can see is that this line is actually parallel with the Hooke's law line. So they're actually parallel. So it will be very easy to draw if you are asked to draw one. So we take another example here. Let's say it's somewhere here. Okay, then it will follow a line parallel. Not so good. Let me draw again. Okay, so it will go parallel. Looks slightly better. It's supposed to be a straight line, yeah. Okay, because it's hard for me to draw on the screen here. So supposed to be a straight line and parallel with the Hooke's law line, yeah. So it will go down like this, and then permanent deformation will be up to this point here. Okay, so let's move on. And you can see that for different kind of material, their graph actually will be different. Okay, if you want to know where's the elastic limit, of course you need to do a test and see whether it go back to the original length or not. But we can say that for the straight line part of the graph, okay, if you continue to perform the experiment and you found that, oh, there's a straight line before this, so this part must be the part where it obeys the Hooke's law, this part must be the part that it obeys the Hooke's law. So afterward, where is the elastic limit, then you have to do the unloading to check. Okay, so strain energy, before that, let's try to make a correction here. I want to remove this word. Let's remove that word. Okay, energy stored in a deformed material is called strain energy, aka elastic potential energy. Also known as, not aka, just short form, aka, elastic potential energy. So when you see strain energy or elastic potential energy, that means that it's something that you have tried to deform it, stretch it, compress it, it store this energy. We say that it store energy because when we let go, right, it will retract, it will extend back. So that's because it has gained some energy, and now it will use that energy to do work. Okay, so there are some details inside here that you need to know. Let's proceed. Okay, so let's say we have a graph of this, and area below this graph will be equivalent to strain energy if the graph is if the energy is found to be below this elastic limit, then we can straight away use half fx. If the graph is for an extension up to this point here, but it's still within the elastic limit, then we have to find the area under the graph. That's by box counting. Okay, so if it is still within the elastic limit, then we will use half fx as the area of that triangle. Okay, then let's look at another graph. Another graph is called the stress strain graph. Stress strain graph is your plot, right? It will actually looks the same because remember, stress is force over area, strain is extension per unit length, therefore it should behave the same. But area under it is called slightly different name. It's called the strain energy per unit volume. It's called strain energy per unit volume. Why is that a strain energy per unit volume and is half sigma epsilon? So to understand that, let's try to extend the sigma and epsilon. I'll just show it up here. Sigma is FOA, stress is FOA, force per unit cross-sectional area, and epsilon is extension per unit original length. So now you look at this thing here, a different color, half fx. So half fx is exactly the same here. And now we focus on AL. AL means cross-sectional area times length. Cross-sectional area times length. So that's like something like this. Cross-sectional area times the length. So what is that actually? Exactly, that's the volume. That's the volume. That's why it's strain energy per unit volume. Okay, strain energy per unit volume. There's different terms, so remember that. So comes to an example. We have wire of cross-sectional area 0.65 mm square, 80 cm, stretch both end by 30 Newton. Calculate the stress on the wire. So you can just use the 30 Newton divided by 0.65 in terms of meter and square, like that. Then you should get the answer of this. And if the extension is 0.12 cm, what is the strain? So we have the original length, so we don't have to change that because the original length is also in terms of cm. So then you should get the answer. Okay, no unit because it's length over length. Calculate the Young modulus. Young modulus will be stress over strain. E equals to stress over strain, okay, which is answer from A and answer from B. Then you get the answer. Oops, sorry. Okay. Last one. What is the strain energy of the stretch wire? Strain energy of the stretch wire. Okay. So this one, of course, we assume that it is within the elastic limit, within the proportionality limit, that it is a straight line. So we have F times X. Okay, we have F times X, which is 30 Newton, half 30 Newton, and the extension is 0.12 times 10 to the power of -2, changing to meter, right? Then you should have the answer. Okay, this one will be your homework, okay, your assignment, yeah. So I'll see you in the next video.